Okay, welcome back everybody to our third lecture, starting to get into the swing of things. So today should be probably the last lecture that's going to be pure math review, and we may get into deriving the fluid mechanics equations at the end of class, or that may be on Thursday. But we're close to the end of the review part. I just want to mention a couple things at the beginning. One is this probably especially applies to people on the physics side, but maybe also to the engineers. Is about the summer NSERC USRA awards. Can you put your hand up if you're familiar with this program, USRAs? A couple people. Okay. So the reason it might apply more to physicists is because engineers you guys are co-op generally, right? So you have a work, next semester will be a work term for you. So which is during the summer?
Yeah.
Right?
Yeah.
So so what a USRA is, it stands for so NSERC is the National Sciences and Engineering Research Council. That's the national funding agency. So it's like in the United States, they have the National Science Foundation, which is NSF, and in Canada, we have NSERC. So it's sort of the governmental funding organization that funds most academic research. And then they have an award called USRA, which is Undergraduate Summer Research Assistantship, or something like that. Maybe this might stand for award. And so what this is it's an opportunity you can just apply for through NSERC, where if you are given the award, basically you get a summer research position that's paid, and you work with one of the faculty at the university. And generally what happens is you can apply for the award. If you get the award, many faculty would be interested in working with you because NSERC pays a good portion of your salary. So it's like a research experience for the undergraduate student, and then for the faculty, it's kind of a cheap to fund research assistant. And the applications for that program are due on February 6th. So if you have any interest in getting involved in oceanography research, climate research, or really anything, feel free to contact me and I'm happy to help with that. It's a really great program. If anyone's interested in a career in sort of university type research, basically all of the Canadians that I know that have gotten faculty positions have at some point done one of these awards. So it's a great opportunity. And the funding is okay. It's the pay for the research position is okay. It used to be better, but the numbers haven't kept pace with inflation. The other thing I just want to mention is that the first assignment, I think I posted it on Friday. Has anyone had a look at it? A few nods. Does anyone have any? So we should cover. So there's one question that we haven't covered the material yet. So does anyone have any questions at this point about the assignment? It's still not due for a little while. Okay. Well, if you do come up with any questions, you can either ask them in class. I'll usually ask at the beginning of class, or you can feel free to send me an email, and either we can address the question over email, or we can make an appointment. Okay. Any questions about anything else at all? Oh, the one last thing is I started posting the YouTube lectures. So probably at this point, it hasn't been super useful to look at them because there's no midterms or anything coming up. But they're all posted on my YouTube channel, which I link to on the Brightspace page. So feel free to go take a look at that if you want to review anything. And I think if nothing else, doing the video lectures will try to encourage me to write larger and more legibly. Okay. All right, so just as a bit of review, so every class I'll do a little bit of review. I kind of did a little bit out of order this time, so we'll do these in a different order. So last time we mostly focused on Taylor's theorem, which in one dimension has this form. And so what Taylor's theorem does is allows us to approximate a function near some base point. This should have been X naught here. And there's different orders that we can make our approximation. So increasing in complexity. The first order would just be taking this base point term and then this linear term. And when I say linear, it's linear in delta x. So as we move, we have some base point x naught. And as we move a distance delta x away from that point, the simplest model of how that function behaves is just these first two terms which is the equation of a straight line if the variable is delta x. But we can make an increasingly accurate and increasingly complex model by including extra terms. I've written here down here the second order term, which is proportional to delta x squared. That's why it's second order, because of that square there. And that's multiplied by the second derivative. And then there's a whole infinite chain of higher and higher terms, which would depend on delta x cubed, delta x to the fourth, and higher derivatives. And these coefficients in front keep changing as well. I'm not going to write the general formula because we won't need it. But basically, all of the higher order terms we're including in this big O notation, where this just means a collection of terms, possibly infinite, in which all of the terms depend on delta x at least to delta x cubed. So it could be to the third power, to the fourth power, etc. And the idea we always have in our minds is that delta x is a small distance. So our base point is a certain location, and we want to look only in the vicinity of that point, so delta x remains small. What that means is when we take higher and higher powers of that small number, those numbers get smaller and smaller. So whatever's contained in this big O error term should be very small compared to the terms that we're keeping. And so, and in the limit that delta x goes to 0, as we get infinitely close to our point of interest, or x naught, this approximation becomes increasingly accurate, and these terms become increasingly dominated. So this is the general form of the theorem. And last class I did an example that showed that the first order Taylor series, which is these first two terms only, that this formula, f of x naught plus delta x times df dx, that's actually the same exact formula that you get if instead of relying on the theorem from calculus, you instead ask, if I want to choose a straight line, so some y equals mx plus b, that models our function f in the two senses that the straight line matches the value of f at the position x naught, and it also matches the slope, then we also arrive at this first order Taylor formula. So sort of the interpretation of the first order Taylor series is that it's the best fit line that matches the value and the slope of the function at a particular point. So now skipping down to the bottom, we also started to talk about vector calculus, and we introduced the notion of the gradient operator, which we denote by this triangle with the vector symbol above it. And this is a vector operator, so you give it so just like the operator d by dx, you give it a function and it gives you back a different function. And the gradient operator is made of the vector, where the three elements of the vector are the partial derivatives with respect to the three coordinate directions. So we have d by dx, d by dy, and d by dz. And you can talk about the gradient either in 2 dimensions or 3 dimensions. So if we were only working in x and y, you have a 2-length vector. You just forget about that last component. And we looked at some of the properties of the gradients in terms of like, what is the interpretation of this thing. And we found that we mentioned 2 major properties. Number 1 is that it's orthogonal to the contour line. So I'm actually going to do an example. I realized I forgot to do, I was taking a look at the video, and I realized I forgot to actually do the example of calculating the gradient of this thing. So we'll just do that first. But so the gradient is a vector, because the operator has vector structure. So you give it a scalar function, it gives you back a vector, and those vectors are orthogonal to the contour lines of the function. Those are the lines along which the function is constant. And so, for example, in this case, we have the function as x squared plus y squared. That's constant on circles, and so the gradient vector of that function is orthogonal to those circles. We'll do that example. And the other point we mentioned was that not only is it orthogonal to the contour lines, but it points in a specific direction. It actually points in the direction of the sharpest increase of f. And we talked about how this has applications, for example, in finding minima of things, finding the minimum value of functions. And this is something, for example, that's done all the time in machine learning. This is sort of beyond the scope of this course, but if you have some experience with machine learning, there's this thing called a loss function. And what you're trying to do is optimize the model by minimizing this loss. Again, if this is not something you're familiar with, don't worry about it. But basically, the gradient tells you the direction of the sharpest increase. And so if you go in the opposite direction, that's the fastest decrease. And so you can use this to find, say, like local maxima and minima of functions. And that's exactly how machine learning models, like for instance ChatGPT, that's exactly how they're trained. Okay, so what I'm going to do at the start is just return to this circle example we did last time, and then we're going to move on to differential equations, which we began last class. But I'll just pause briefly at the review. Does anyone have any questions about the review? All right. Okay. So I just want to complete this example that I sort of overlooked last time. So let's say calculate the gradient. So the gradient of f is equal to df dx, df dy. And so the x partial derivative of this is just 2x. The y partial derivative is 2y. And so this is 2 outside of xy. And we would usually denote that as 2 times the vector x, the position vector in the plane. And so this is how we can see that the gradient vector is orthogonal to the contour lines, because, for example, if we wanted to look at the contour lines for f equals 1, it would be the circle of unit radius, because x squared plus y squared equals 1. That's the unit circle. And so our gradient is the position vector. And so we usually, when we draw gradient vectors, we draw the base point of the vectors at the location we've calculated the gradient. So rather than drawing the center, and then we draw our vector. So this our exposition vector points radially outward. So here's our gradient. And if we wanted to draw the gradient over here, it would look like this, etc. And another thing that we can see is that as these circles get bigger and bigger, so if instead we were looking for f equals 4, that would be the circle of radius 2. Then now, our value of x has gotten larger because we're looking at a circle of larger radius. And so as we go out further, these gradient vectors get longer. So the direction is always orthogonal to the contour values, to the contour lines, and then the size of the vector depends on exactly where you are and exactly on the formula for the gradient, which you derive by taking the derivatives. Okay, so that's just a little correction from last class that I missed. Okay, so now we're moving on to differential equations. And we talked last time, to about the end of class, about how when you take a course, there's usually a course in your program that's just called differential equations, or maybe ordinary differential equations. And what you mostly learn is special tricks for solving certain classes of differential equations. Usually each section of the course is called like separable equations, or linear equations, or Bernoulli equations, or whatever. And then there are specific techniques or tricks that you can use to solve equations of that type. And so what I'm focusing on here is not that at all, and instead, how do you solve equations when there is no trick that you learned? So if the equation does not fall into a category where any one of those techniques works, what do you do? And generally, what you do is like solve it on a computer, and we're going to talk about exactly how you do that. So in the notes, this is 2.7, differential equations. Okay. So last time, we talked about how f equals ma is really a differential equation because a is the second derivative of the position vector x, which is a function of time. So when you have Newton's law, really the usefulness of Newton's law is that if you know something about the force involved, you have to use some physical reasoning to determine what the force is. Then if you could solve this differential equation of f equals m times d squared x dt squared, then that the solution, so this x of t is the particle position, which is the solution of the ODE. And so if we're able to solve this equation, then that's very a good thing, because we then have a prediction for what the particle position is going to be at all future times. And that's really the essence of differential equations, is in the prediction problem mostly. So like when we do, for example, I think I mentioned last time, numerical weather prediction or just weather forecasting, we have sort of complicated differential equations that describe the atmosphere, and what we want to know is what's the solution of that for what the atmosphere will look like, maybe in terms of winds, temperature, precipitation, a couple of days into the future. And so what they do is they take some differential equation that's formally somehow similar to this, but much more complicated in practice, and they want to make a solution of that to give a prediction for the future. So we're going to do a simple example, and we're going to do it two ways. One, using an exact solution, using one of these simple tricks. And then second, how would we do it on a computer, which would be more applicable to problems like weather prediction. So let's just take a simple example here. And so the equation of a falling particle. So in this case, so we have something like a ball, and then the ball's falling. So it's falling under the influence of gravity, and so the force, the gravitational force on that ball is just mg. And later we're going to think about air resistance. And so air resistance is when the equation gets more complicated, and we're going to have to use a computer. But right now let's just think about a ball falling without any air resistance. So the only force on that particle is going to be the mass times the gravitational constant, which is just 9.8, times minus z hat. So we have always have to include our direction. The force is a vector quantity, and so there's a force pointing in the negative z direction pulling on this particle. And so we're calling here, so x of t is the vector that contains x of t, y of t, z of t, which are the three components of the position. And so taking the z component of this equation, the only force is in the z direction. So we get the force is minus mg z hat equals m d squared x dt squared. And the z component of this equation is minus mg equals m d squared z dt squared. So we can cancel our m's on both sides, and we just get d squared z by dt squared equals minus g. So this is a second order equation, but we can write it as, it's so simple that we can write it as a first order equation very easily we usually define w as the vertical component of the velocity. So w here is dz dt, it's the rate of change of the vertical position of the particle. And so making this substitution, we get the equation dw dt equals minus g. And so this is the equation we're going to start with. It's ridiculously simple, but we're going to use it to illustrate sort of a point about how we can solve equations on the computer versus exactly. Okay, so let's pause there for a minute. So, can anyone tell me what's the solution of this differential equation for w of t? What's the answer?
W naught minus gt.
Correct. Yes, that's right. And how did you determine that?
By using separation of variables, or
separation. You can even just integrate it directly, but if you want, you can cross multiply it first.
Solution to
yeah. Okay, so that's right. So let's solve this thing exactly first. And there's one point that I actually forgot to make. I'll just make now. So actually, when we write down a differential equation like this equation saying that the rate of change of the vertical velocity is equal to just minus g, just minus a constant. This doesn't completely specify the behavior of the system yet. We also have to supply the initial conditions, which is probably familiar from your class in differential equations. So a differential equation alone does not fully determine the solution. And we must also supply initial conditions. And that really makes sense. Because, of course, to make a prediction about what the weather or the state of the atmosphere is going to be like tomorrow, what the state of the atmosphere is currently would be an important part of that calculation. So this equation tells us the rate of change of W. And if we know the initial state and we know how it's changing, we know where it started and we know how it's changing, so from that we can predict everything about how it's going to behave in the future. So for our example, we'll say the ball starts from rest at t equals 0. And so this is mathematically the condition that W of t equals 0 is equal to 0. So once we have the equation and we have the initial conditions, now we have enough information to completely constrain what the velocity is going to be like in the future. So here's how we do the exact solution. Very, very simple in this case. We have dw dt equals minus g. And we can integrate both sides. And I'm going to integrate dw dt prime using a dummy variable t prime equals this integral. And I'm going to integrate from t equals 0 to t equals t. And now this integral is easy to carry out because it's just the integral of a derivative. So what we get here is the value of w at the endpoint, so w of t minus w of 0. And that equals minus g times t minus 0. Because we've assumed the particle starts from rest, we just get here w of t is equal to minus gt. And so this is a kind of a typical trick. You can think of this as direct integration. What was suggested from the crowd was do separation of variables. If you wanted to do separation of variables, you could do it like this: dw dt equals minus g, cross multiplied by your dt. This might be sort of a more typical method, and then you can integrate both of these sides, and you get the same answer. So two equivalent ways. They're formally equivalent. And because this equation is so simple, we're able to get an exact solution. Okay. But what's going to happen if we make our equation more complicated? So next, let's add air resistance. So now we have our ball. It's being pulled down with a force mg, and it also has a drag force which opposes the motion. And what the formula for the drag force is sort of complicated to say exactly, because when you drop an object, what's really happening is it's falling through air, and the air is flowing around the object. And actually, the nature of that flow can depend strongly on the speed. In other courses that are on sort of pure fluid mechanics, you might focus on this a lot more, actually, computing what the flow looks like around a falling sphere and deriving the drag force from first principles. But what I'll say is, it's quite complicated. There's not really, and especially at high velocities, the flow around the ball can become very complicated and turbulent. And especially if you consider something like a golf ball, if anybody plays golf, the golf ball has this very complicated shape, it's rotating, it's going very fast, and there's actually turbulent flow and pressure differences on both sides of the ball, and so the drag forces that act on a ball are quite complicated. You can also see this because if you are interested in any sport like baseball, or I guess it happens in golf, or what's the most famous example? I was thinking about a second ago.
Ping pong?
Ping pong, sure too, with spin, with curves, like curve balls happen. Does somebody say something?
Frisbee? Like
Frisbee, it's a different shape, but yes. So these things curve in the air, right? And that's because of these fluid forces that are acting on the ball. And so obviously it can get pretty complicated. What's often done in physics is we have a sort of a simple approximation for how the drag works. And a very common approximation is that the drag force is equal to minus alpha times w squared z hat. So meaning it's actually we should say plus because it's pointing upward. So for a falling ball, we have an upward force, and then the force is proportional to the square of the velocity, and then this is called a drag coefficient. So as the speed gets faster, the drag force gets faster quadratic. You double the speed, the drag force goes up by a factor of 4. And this is not the only model that's used for drag. Often there's a model where you have a linear term and a quadratic term, and in reality, you have to solve a complicated fluid dynamics problem to understand the drag. But let's just use this simple model for now. So in this case now, our net force is equal to minus mg z hat, that's our gravitational force, plus alpha w squared z hat is our drag force. And so our F equals ma equation gives us m times dw dt is equal to minus mg plus alpha w squared. And if we want, we can cancel out the m's and get minus g plus alpha over m w squared. Okay, so there's lots of analysis that you can do with this formula. For example, you can solve for the terminal velocity. So that the terminal velocity is when the ball is falling quickly enough that the drag force actually exactly cancels out gravity. So that means there's no more net force. Gravity is canceled by drag, and so then you start to fall at a constant speed. I think this happens to, like, people jumping out of, like, what is it called? Skydiving. When you're skydiving, you reach terminal velocity. So you can do all kinds of analysis on this. But I'll just ask the class, does anyone have any idea like how to solve this equation exactly? Yeah.
You would employ separate rules. Solution again by just dividing over and then dividing over the equation and get 1 on one side and then integrate with respect to time.
So you want to do what exactly?
Divide over by negative g plus alpha over m omega squared, or w squared, and then you can integrate with respect to time, and you get I believe an arctan solution, which is a bit weird, but
so you've seen this exact equation before,
yeah,
and you know
it
happens to have an exact solution. This particular one.
Yeah.
Okay. So
you can't integrate for position, but you can get the velocity with respect to time.
Okay. So that's a good point, although it's a little bit derailing. But so this equation is nonlinear. Is the key thing. So when we started with this equation here, the right-hand side is actually even sublinear. It doesn't even depend on w. But if you had a w here, it'd be linear. And in general, all linear differential equations always have an exact solution. But nonlinear equations, when you have a w here, or w to a higher power, so w squared, in general, they don't tend to have exact solutions. So it actually turns out that this particular one does, but the reason is because what Ben has suggested here is write this as dw divided by minus g plus alpha over m w squared equals dt, and then integrate both sides. And it turns out you can actually do this. But one can imagine, I could make this even a slightly more complicated, maybe add a linear drag term or add a more complicated form. And what comes down to having an analytical solution, what we mean when we say we have an analytical or exact solution to the equation, is that this integral has an antiderivative. That you can actually do this integral by hand and get a function out. And it turns out that you can for this one, but for even slightly more complicated versions, you can. You can easily create problems where this integral has no antiderivative. And so what we'll do is proceeding as if we didn't happen to know how to do this integral. So if you don't happen to know how to do this integral, or if you were presented with one that doesn't have an antiderivative, can't be done analytically, how would we solve this? So very, very nice for knowing the exact solution, but it's sort of a special case even still. So we can still think about what would we do? So this equation, so as I said, so this equation is nonlinear due to the quadratic drag term minus, or sorry, plus alpha over m w squared. Linear equations always have an exact solution. So linear equations always have an exact solution, but nonlinear equations, the vast majority, do not have any exact solution, at least that is known. It's possible that they will be discovered in the future, but right now we don't know anything. So nonlinear equations generally do not have exact solutions. So given that, how can we predict WT in the future? I'll make a parenthetical remark. This particular one, this particular ODE happens to have an exact solution. But this is lucky. So we're looking for general methods that will work for any differential equation that doesn't rely on some particular integral existing or having an antiderivative or what have you. Okay, so how do we do this? So there's a sort of a set of methods. So the answer is called numerical methods, or numerical solutions. And so we're going to focus here. There are a particular example of a numerical method called Euler's method. So this is the next section called Euler's method. So there are many different ways of obtaining solutions to differential equations that do not have exact solutions. And Euler's method is the simplest of them, but there are several courses, I think mostly in the math department, that discuss a whole set of methods that differ based on their details and also their accuracy, also their computational cost. For doing this, to try to make a prediction for W of t for the whole future. And we're just going to focus on the very simplest one, which illustrates the idea without getting into many complexities. So the idea of Euler's method is, so Euler's method gives an approximate solution to any ODE. This is any ODE. This is an approximate solution by discretizing time. I'll explain what this means, but I just want to make clear, first of all, what I mean by approximate. So I'll explain now in a second what I mean by discretizing time. But when we say approximate, it's a very good kind of approximation in that the kind of approximations that we're going to drive now momentarily are approximations that can be systematically improved. So you can make the approximation as accurate as you like by changing your computer program in a very sort of simple way. And so we'll see how we do this. So, so to discretize time, we break up our time interval. Let's say we have a time interval t, and we'll say t is in. So this little epsilon e symbol means that t is in the set from 0 to, let's say, 10 seconds. So let's say we want to predict the fall velocity of this particle from t equals 0 when it's at rest to 10 seconds in the future. What we do is we take this time interval and we break it up into small pieces of size delta t. And then delta t is a parameter that we choose. So as an example, just to pick a sort of arbitrary, we could say delta t is equal to 0.1 seconds. So what does that look like? So what this looks like is, let's say here's our line of time. So this would be t equals 0 on this side, and over here on the end, we might have t equals 10 seconds, 0 seconds and 10 seconds. And by discretizing it into these little chunks delta t, all I mean is you break it up into these little pieces, where this would be 0.1 seconds, 0.2, 0.3, and then dot, dot, dot. And at the end, we would have here 9.8 seconds, 9.9 seconds, and then 10 seconds. And so each one of these little pieces is of width delta t. Okay. So once we've done this, so this is called discretization, because we've taken the continuous interval going from 0 to 0 to 10, sorry, which in principle has an infinite number of moments, right? Like how many real numbers are there between 0 and 10? There's obviously an infinite amount. And we've taken that infinite continuum and we've made it discrete. That's why it's called discretization. And so we've made it into these discrete chunks, 0.1, 0.2, 0.3, etc. So next, we approximate the derivative dw dt using the definition of the derivative. So, normally, we would have dw dt is defined as the limit, as delta t goes to 0, of w of t plus delta t minus w of t divided by delta t. So this is the normal definition of the derivative from first year calculus. And what we're going to do is we're going to make an approximately equal sign here. And we're going to say, rather than treating the limit formally as delta t goes to exactly 0, we're going to take delta t to be a finite number, but then hopefully it's small enough, we're going to choose delta t to be small enough, that even though it's not actually 0, our limit, this formula is still a good approximation to the limit. So we're going to write approximately equals here w of t plus delta t minus w of t divided by delta t. So these two formulas are exactly the same, except we just dropped the limit here. So we're not going to take any formal limit as t goes to 0, as delta t goes to 0. We're going to take delta t equals 0.1 seconds, calculate this, and this is really the slope of a secant line rather than the slope of the tangent line for the derivative. But we know that as delta t gets smaller and smaller, the secant line converges to the tangent line, and so this expression will converge to the derivative in the limit that delta t goes to 0. Okay. And if you play around with this, I would say on a computer, what you'll find is that if delta t is sufficiently small, you'll get a very, very similar answer from this finite computation versus this calculus computation involving the limit. Okay. So under this approximation, our ordinary differential equation, ODE, becomes, so remember we had dw dt equals minus g plus alpha over m w squared. So our new version of this is w at t plus delta t minus w of t divided by delta t equals minus g plus alpha over m w squared. And so now this equation it's really approximate, but sort of in the framework of Euler's method, we can either write an approximate here or say this is the model. And so this is a approximation to the differential equation that becomes exactly accurate as delta t goes to 0. Okay, and so now to make our lives a little bit easier and to see how this actually very, very quickly becomes an algorithm that can be implemented either by hand or on a computer to predict the future of W. I'm going to make a little notation here. So our time discretization is we have t. So our time discretization is t is now in the discrete set 0, 0.1, 0.2, 9.9, 10. And we're going to define the notation that t sub I is defined to be I times delta t. So rather than saying it's 0.1, 0.2, 0.3, we're going to say it's the first time step, the second time step. So we have here, so for example, t sub 0 would just be 0 times delta t is 0. T sub 1, 1 times delta t would be equal to delta t, which is 0.1 seconds. T2, 0.2 seconds, dot, dot, dot. And then t capital N, we had to work out how many time points we had, but it'd be, so n minus 1 would be 9.9 seconds. And t capital N equals 10 seconds. The idea is capital N equals total number of time points. So we'll define this notation, so our times are called ti, and then similarly, we define w sub I is defined as our falling speed, our real function, of ti. And so this is the velocity at the particular time ti. We're going to call that wi. So our initial condition is w of t equals 0, which we're calling W0, and that equals 0. And we have W, so W0 is W of t equals 0, W1 is W of t1, W2 is W of t2, etc. Okay, so with this new notation, so we haven't done any calculation or anything, but just with this new notation, we can now rewrite. So with this new notation, our equation becomes so W of t plus delta t. So this would be W if we think about Wi is equal to W of t sub I, then our equation is now W of I plus 1 minus Wi divided by delta t is equal to minus g plus alpha over m Wi squared. So our approximation to the derivative now gives us a sort of an initial equation involving these I indices. And it relates, the equation relates Wi plus 1. So if Wi is the velocity at some particular time ti, then Wi plus 1 is the velocity at the next time step. And so this is the way that we do numerical solutions. We think of things in terms of time steps, and we're often looking at what's happening one step in the future of where we are now. So we want to relate Wi plus 1 to Wi. And so we can rearrange this, just multiply by delta t and bring the Wi across. And so we can rearrange. And we get Wi plus 1 equals Wi plus delta t multiplied by minus g plus alpha over m Wi squared. And this equation here, this is actually called Euler's method. And it's worth it to pause and just think for a second about what this equation actually does, which is, it says, so the right-hand side of this equation, the critical thing about this right-hand side is that it only involves Wi. So we think of I as some particular time. I could be, for example, 0. It only involves Wi, and if we happened to know Wi, we could work out this number on the right-hand side. If we knew what Wi was, and I gave you a value for alpha, a value for m, and so forth, you could calculate this number for a particular choice of delta t. And that would tell us what is Wi plus 1, what's the velocity at the next time step. And then we can repeat the cycle. We could take that value of Wi plus 1, move one step into the future, then we'll know the right-hand side again. You can predict the left-hand side, and this way we can step the solution forward in time. That's called time stepping, and it's also called a marching scheme. The idea of you're sort of like soldiers marching is the advancement of time or whatever. So this formula allows us to step by step construct the value of W at all of these discrete times in the future. So this equation allows us to compute step by step the values of Wi for all future times. And so it's helpful to just do this as a concrete example. And the way this works is we start from W0. We're always given some initial condition. You need to know that. And then when you know the initial condition, you can calculate this right-hand side. the knowledge of W0 will allow you to compute W1, then W1 allows you to compute W2, and so forth. You can calculate as many steps as you like. So for our equation, it looks like this. So let's set okay. All right. So we have the equation here. So for I equals 0, we get the following equation. So starting at I equals 0, our equation is W1 is equal to W0 plus delta T times minus G plus alpha over M W0 squared. Now, because we know from our initial conditions that W0 is 0, so we're saying we start from rest, so the initial value of W is 0. So we just get that working on the right-hand side, that term is 0, this term is 0, so we just get minus G times delta T, and so that's W1. So W1 equals minus G times delta T. This equation makes a ton of sense. So you start from rest, no velocity. There's no drag force acting on the system yet because you haven't started falling. So after a small time delta t, the ball has picked up a velocity that's equal to the acceleration it's been pulled down with times the small little interval of time that gravity has been pulling. So the strength of the acceleration multiplied by the time that the acceleration has been acting. So next, we can look at the equation for I equals 1. So for I equals 1, we have I plus 1 is 2, so we have W2 equals W1 plus delta T minus G plus alpha over M W1 squared. And now it starts to get a little bit more complicated, but we can plug in our solution for W1 in here. So we plug in W1 equals minus G delta T, and we get W2 equals minus G delta T minus G delta T from this term, plus delta T alpha over M times minus G delta T squared. So all we've done here is plug in minus G delta T in two places, or for W1 here and for W1 here. And so what we get is these two terms can combine, minus 2 G delta T plus alpha G squared over M delta T cubed. So this is our equation for W2. So W1 equals this, W2 equals that. Okay, and again, we can interpret this equation. I think it makes a lot of sense. So the ball's velocity now is, again, it's equal to G minus G times 2 delta T. So now we've waited twice as long because we're on time step number 2. And so the falling velocity is this first term is G times minus 2 delta T. So that's just what's happened because of the acceleration. And then we're adding on a term. So the velocity is negative. So when we add a positive number here, that's going to make it a weaker velocity. And now this extra term that's weakening the velocity is now proportional to the drag coefficient. So we have the speed of the ball that's just falling under pure acceleration, plus a term that weakens that velocity that's somehow related to the drag. And so now I've worked this out in symbols here. But if you wanted to plug in numbers, you could say W1 is minus 9.8 meters per second squared times 0.1 seconds is minus 0.98 meters per second. And then you could do the same thing down here. I would have to give you a number for the drag coefficient and so forth and the mass. But then you could calculate this as a number, and it will be slightly less than twice this number. And so this method, you can continue this to I equals 2, I equals 3, and so on, and you can keep running this same trick back and forth until you reach whatever time you want to know. So for example, 10 seconds. And so on the first assignment, you get a chance to do this for a very, very simple equation of just exponential decay, just radioactive decay, which has the equation the NDT equals minus lambda n. So the solution, the exact solution is n of t equals n naught e to the minus lambda t, and you get to compare this exact solution to a solution that you construct using this method. And so it should seem, I think, pretty natural that this thing is really a loop, right? So you calculate one step, then you take the answer from that step and plug it into the next step, and so it fits very naturally into the structure of a for loop in Python or any computing language. And so there's actually a code. You can see it in the notes. There's also on Brightspace now there's a section called code. You can get a couple of notebooks that give some sample codes that can help with the assignment. And so I think I implement this this exact equation, and you can modify that code to work with this equation. Okay, and so the nice thing about this is it relies on no knowledge of antiderivatives. You don't need to know any Calculus 1001 tricks of how to integrate arctans or whatever. And no matter how complicated a right-hand side I gave you, whatever stuff was on this right-hand side, I could make this increasingly complicated, add a whole bunch of terms, and you could always use this method. And the idea is that this is an approximate solution, but the solution will get more and more accurate as you shrink your delta t down. And in the limit, at that delta t becomes extremely small, it becomes extremely accurate, arbitrarily accurate. So when we say that these are approximate solutions, that's true, that's very strictly true, but what that means is when we say they're approximate for any finite delta t, but we can always make that approximation better and better to any desired accuracy, but it's making our delta t smaller and smaller. And so generally, when we get equations that come from fluid dynamics, they tend to be nonlinear, they tend to be unsolvable using these classical tricks that you learn in ordinary differential equations classes. But they can always be solved using either Euler's method or a very, very similar method. And so this whole idea of discretizing, breaking the time up into different time pieces, different time chunks, and then writing down sort of an iterative loop-based method for computing the solution step by step. This is a very general procedure that can be used for any equation that you might encounter. Okay, so I suggest when you do the assignment, you can, if this isn't, you take a stab at it on your own if you want, but you can also take a look at the code, and that might be helpful for seeing the loop structure that's appropriate for doing this kind of thing. Okay, so that's it for Euler's method and differential equations. And now the last part of the class I'm going to move on, I think we can cover it in the last 10 minutes, it's going to be on dimensional analysis. But I'll just pause here briefly. Does anyone have any questions about Euler's method or numerical solutions or nature of the approximation or anything like that? Okay. All right. Okay. 2.8 dimensional analysis. All right, so everybody here has probably taken physics 1050 or 1020 or those early year physics courses or some engineering equivalent, if you maybe transferred or anything. And so when we do these first year physics courses, especially when you're writing your lab notebooks and on tests and stuff, you're constantly being told, at least this was my experience, to check your units and always write down your units. And if you don't write down your units, you get -1 or whatever. And I remember it was definitely my attitude at the time that this was really sort of annoying, and it seemed kind of pointless. And like, if you're solving for a velocity, like it's obviously meters per second squared. Who cares? Why do you need to constantly say this? That's true for really simple problems, like ballistic motion problems, things like that, where there's only maybe velocity and time and distance involved. It's very difficult to make a mistake in terms of the units. But when you get into sort of more complex types of physics, like fluid dynamics, electromagnetism is really bad for this, thermodynamics. The sets of units that get involved are much more complex. And it turns out that it's extremely useful to think about the units of the quantities that show up in your problem for two reasons. So the first reason is that if you keep track of your units, and then at the end of your calculation, you are supposed to have a time, but your answer is in meters, then you must have done something wrong. So it's a way to catch errors. But an even more important reason why it's important to pay attention to units is that it can help you interpret the physical meaning of various parameters or variables that may occur in your equations. So I'm just going to show one example, and then in this course, so both on the first assignment and I guarantee on one or both of the midterms and the final, there'll be some kind of question involving units. So I just want to make a distinction here. Paying attention to units is valuable for one, catching errors, but more importantly, interpreting meaning. And what I mean by interpreting meaning is you sometimes may have a variable or a parameter that you don't really know what it means or where it came from, but if it has units of meters per second, like maybe it doesn't look like a velocity, but if it has units of meters per second, it's really physically, it has to be some kind of velocity of something. Maybe it's the velocity of a wave, or maybe it's a particle, or maybe it's the velocity of a coordinate system. And so by looking at the units, you can sort of help yourself interpret, like, what's the physical meaning of this thing. But there are two related concepts, but they're slightly different. Are units and dimensions, or dimension. So a unit is something that literally a unit of measure that we use to quantify something. So this rod is this many meters long. So we have some universal standard at the Institute for Standards that defines what a meter is. So a unit would be something like meters, meters per second squared, whatever. And any quantity can be expressed in any number of different unit sets. So for example, velocity can be meters per second, kilometers per hour, other ones, astrophysical units. And so there's many different ways to represent any one quantity in terms of units. So what a dimension is sort of a more general version. And dimension refers to the type of quantity that you're measuring. So for example, the dimension of a length, or the dimension of the length of a road, we call that the dimensions of length. So we have dimensions of length, dimensions of mass, dimensions of time, and then often also dimensions of temperature, we use the symbol theta, and dimensions of electric charge, or Q. And so a velocity will always have dimensions of length per time. So you can represent that in meters per second or kilometers per hour if you want, but it will always be length per time. And so dimensions are an easier way of keeping track of the physical meaning. Is something a velocity? Is something an acceleration? Without having to worry about the particular system of units that you're using, whether it's SI units or astrophysical units or whatever. And although there are infinitely many choices for units, every quantity has exactly one set of dimensions. So for example, let's compute the dimensions of kinetic energy. And so the symbol we use for this is the square box brackets. So these square box brackets means dimensions of K. So how can we determine what are the dimensions in terms of length, mass, time, temperature, electric charge of kinetic energy? What we do is we start from the formula for that thing. So from the formula, the usual formula for kinetic energy is K is 1/2 mv squared. So what we're going to do to determine the dimensions is we're going to take the box of both sides. So take the dimensions of the whole equation, and so we get the dimensions of K. And when you take the dimensions of a product, it's just the product of the dimensions of each, just like with units, it's the product of the dimensions of all of the factors. So we get here the dimensions of the factor 1/2, the dimensions of the particle mass, and dimensions of velocity squared. So any pure number is dimensionless, and so we call that equals to 1. If something has no dimensions, we say it just equals 1. Mass has unit dimensions of capital M, and velocity has dimensions of capital L divided by capital T, and because we have a square velocity, it's squared. And so our final answer here, take it to the bigger board, is that the dimensions of kinetic energy are equal to mass times length squared per time squared. And for something like kinetic energy, it's not that complicated, but especially engineers might have seen things like viscosity. Like you might see dynamic and kinematic viscosity. If you haven't, we'll see them in this course. And for those things, like what are the dimensions of pressure? What are the dimensions of entropy? When you get to more complicated quantities that are less intuitive than a velocity or a distance, this is very, very useful for figuring out what the dimensions are. So I'll do one more example. So consider Newton's law of gravity. So we have F equals G m1 m2 over r squared. So probably we've all seen this equation at some point, maybe in high school even. But most people probably don't offhand remember what are the definitions of the Newton's G constant. Right? Most people don't remember. So how can we figure that out? So what are the dimensions of Newton's G constant? The key thing is that whenever you have an equation, the equation says obviously both sides are equal, they're the same equivalent, they're the same thing. So whenever you have an equation, both sides have to have the same dimensions. And also whenever you have different terms that are added, each term that is added, they also have to have the exact same dimensions. Because you can't add like a time to a length, for example. You can only add velocity to velocity, time to time. So both of these sides have to have the same dimensions. So the dimensions of F are equal to the dimensions of G m1, m2 over r squared. So F has dimensions of ma, and that's from Newton's second law. And so that's mass times length per time squared. And over here, we get the dimensions of the G constant times 2 masses, so that's mass squared, divided by length squared. Also, something I just want to point out that's it's important not to mix up is that the capital M always stands for mass, and it's easy to confuse with meters. So just be careful about mass and meters. That's a very easy mistake to make. That's blending dimensions and units. But so here the last equation we'll write is, so just putting those two sides together, we have ml over time squared, mass times acceleration, equals dimensions of G times mass squared over length squared. We can cancel one factor of mass and rearrange, and we get G is, make sure I did this right, is we get 3 factors of L here, 2 here, and then 1 there. So we get L cubed over times squared, and then one of our masses was left out and not canceled. And so our dimensions of the G constant, we can derive them from this. Length cubed divided by mass times time squared. And if you do a Google search, you'll find that G is equal to 6.67 times 10 to the minus 11 meters cubed per kilogram second squared. And so this is exactly this. So this is a unit of length, unit of mass, square unit of time. And so this calculation that we did, where we just started from the equations that are involved, and we derived what units have to be, that's fully consistent with something that you would look up in a book or article. Okay, so that's it for today, and that's the end of the math review. And so next time, we're going to start talking about fluid mechanics proper, and get on our road to deriving the Navier-Stokes equation and the other equations that we're going to need to explore all kinds of ocean phenomena. Okay, great. Well, everybody have a good couple of days, and I will see you on Thursday.
Thank you.
Thank you.
Go.
Did I ever? No, I sent you an email just on like the Discord and everything like so.
I'm resigning them.
Why? I just like to be like.
I mean, it wouldn't